Thank you for joining us today. My name is Ed Tate. I'm responsible for thermal applications and system modeling at Exa, and I'll be speaking to you today about thermal management for electric vehicles. Now, my background is I've worked with electrification of vehicles for more than 25 years, and one of the key challenges in electrification is managing these relatively sensitive parts that are in an EV so that you can get the maximum performance. And with Exa's thermal solutions, it's possible to engineer a better EV, and better EV means more range, more performance, and more durability. To help introduce this, we'd like to discuss some of the trends that are happening right now and the impact that they will have on things that will be done by OEMs and startups in the near future. The first one is taking a look at the investment in vehicle electrification. There's a lot of publicly announced investment that's going to be happening in the next decade or so. And this investment's being done globally, the US, China, and the biggest investment by far that's been made public is out of Germany. And these investments are focused on things such as capital for plants, development and R&D facilities, and overall product improvements and changes to make it possible to electrify our fleets. Looking at the timeline between today and the next decade, it's expected by customers that EVs are going to be cost competitive with the cars that they buy today. And some of automakers have already announced that they have very, very large-scale intentions to make the bulk of their fleet, if not their entire fleet, electrified by the 2030s. So in automotive terms, this is actually very, very soon because the design decisions that drive things that happen in the 2020s are already being made today. And governments are also driving consumers to buy these EVs through incentives and regulations on how they're going to be used. Now, the reason a lot of this is happening is there's been a desire for EVs for a long time. And the biggest thing that's happened is in the past 20 years, the EVs have gone from something which could go maybe what you would do as a daily drive to something that could satisfy almost all the needs that somebody has. Mass markets for EVs really become possible about 200 miles of range. And that's what we've seen by the makers that have been successful in starting to sell these vehicles. Now, this didn't start this way. When the first EVs were made, more than 100 years ago, we were looking at vehicles that were extremely limited, had very short ranges, and very limited production runs. The steps to get to a high volume production EV today have had a couple of milestones along the way. One of the milestones was the introduction in the 80s of the EV1. That was a 100-mile range vehicle. That was a real full performance vehicle. And probably the biggest change that happened was the introduction of the luxury EVs by Tesla, which hit very large production numbers and showed that it is possible to sell these vehicles into a market that is willing to buy them. Now, what's changed? So in the past decade, what has changed has been the range that an EV can achieve, its cost, and its durability. All the things that technically make it able to satisfy what a consumer needs. To make that happen, there's a lot of technologies that have had a change in automotive to get there. The first set of changes got you to about 100 miles of range and started with structural improvements to make lighter weight vehicles, aerodynamic improvements, which is something Exa is great at helping cars out on, power electronics, which made electric machines efficient over a broad operating range. But that still wasn't enough. 100 miles of range was not enough to really satisfy customers. Other technologies had to be brought in. High efficiency electric machines that worked over a broad range of conditions, much smaller, much lighter than their predecessors. Most importantly, battery chemistry. After long, long development periods, we finally have battery chemistries that are really capable of working in a car for its life. And on top of that, the control systems to manage the energy to efficiently balance where all that power is going to go. For example, balancing what happens between the cabin, the batteries, and the driveline. Thermal analysis is the key to making all of these technologies work together. And in fact, each one of these technologies has particular sensitivities to what happens thermally in the vehicle. So this is the things that have happened. But there's challenges to get to the next step. And those challenges represent opportunities. So for example, with EV, the design challenges that we have are range. That's almost at the point it's completely comparable to an existing vehicle. So you can purchase an EV today at a reasonable price range that almost gets the range that's required that a gasoline vehicle can have. And in fact, this can be a more fun to drive vehicle. You're looking at something which accelerates better and feels better on the road than a comparable car. The cost, just a little bit more than you're looking at for the existing ICE today. And then the big one that pays off for you is once you buy one, the cost to refill and the convenience of refilling is a wildly different experience than you have with a gas car. The cost of operation is much lower in maintenance. The cost of operation is much lower in terms of the energy you have to consume. Now, to take a look at things, let's look at how people drive their cars. So if you look at the drivers that are out there, there are a handful of drivers that at some point or another need to drive about 1,200 miles on a given day. Now, I'm from Michigan. I've actually done this trip, so I can verify this is something that does happen. And it pretty much is done where the vehicle is operated almost 24 hours to go from a place like Michigan to a wonderful place like Florida in late winter, when you'd like to have a little bit of additional sun. But that's not the person you have to satisfy to make a good EV. And in fact, to show how difficult it is, the image up there on the right shows you how much battery would be required to move a car like the one we're showing here, which is Exa's internal vehicle, about 1,200 miles. The batteries would completely fill the car and make it impossible to do anything except move those batteries. And you can compare it to the amount of gasoline, which represents a couple of refills on the tank, that would be put into that vehicle. And it's quite a lot more battery that's required. You know, the batteries themselves would weigh more than the car to make this happen. So the good news is that's only an occasional thing that needs to happen. The vast majority of vehicles drive less than 200 miles a day. And that's 98% of drivers. If they start the car, they're going to go less than 200 miles. And to get 200 miles of range, today that can be bought for about $15,000 worth of battery power, or about 6 gallons of gasoline to get that equivalent. So you can see there's still some disadvantages. It doesn't take that big of a gas tank to hold the gas, and it takes a lot of the car's volume to hold that battery pack. Now, the battery pack adds weight to the car, so this is one of the design challenges that's going to be in making the EV work effectively. And it takes up that additional volume, which changes how the vehicle has to be packaged internally. Additionally, for very small ranges, and there's vehicles that take advantage of this, like the plug-in hybrids like the Volt, they put in a smaller battery pack which provides pure electric operation for about 30, 40 miles of range. And that satisfies the typical driver in the U.S. so they can completely operate their vehicle on gasoline with their usual driving habits. So with this kind of usage, now the challenge is how to get the EV fully cost competitive. So an EV powertrain costs about $15,000 to $20,000 more than a comparable ICE in today. And it's expected that sometime in the 2020s, the cost of all these parts, the battery pack, the power electronics, and the electric machine, will be on parity with the cost of the internal combustion engine that we use today. But there's challenges. Putting a battery into a car is not a simple process because batteries are actually very sensitive to the environment they operate in. If they're too cold, they basically don't provide the power that's necessary to move the car. And if they get too hot, they begin to lose their life. They effectively wear in heat. And if they get extremely hot, they can potentially have a catastrophic failure. So from the thermal system, this needs to be managed in an ideal range. And actually, it's pretty close to the temperature range a human feels comfortable in where the battery works. The reason that you have these temperature constraints is because as the battery starts to get hotter, there's accelerated aging, there's additional things that may happen inside the battery that are undesirable. As the temperature spread in the battery pack gets larger, that causes the batteries to actually charge and discharge at different rates, so the pack appears to be smaller and potentially wears faster. And when the battery is cold, the power levels and the energy that's available from it drop off. And finally, if it gets extremely cold, there's another set of reactions that can occur inside the battery. Now, the battery is not the only thing that has durability issues. The inverter and the motor both are sensitive to the temperatures they operate at. If the power electronics get too hot, they can very suddenly fail catastrophically. It's important to keep those cool. The motor. The reason an EV can be such a fun vehicle to drive is because for very short periods of time, you see the term up here for temporary torque, it can produce a very, very large amount of torque. However, it quickly heats up, and as it heats up, the temperatures have to be dropped. This is another one of the thermal challenges, that by properly managing the temperatures in the motor, smaller motors can provide a better driving experience and the whole vehicle benefits. Additionally, people aren't used to thinking of their cars as doing anything when they're turned off, but EVs are going to have parts of them that are running more than in a conventional vehicle. And the reason for this is that the vehicle will typically be plugged in the whole time it's at home. That could be 12, 16 hours a day. And an EV and an ICE only have the full system running when the car is on the road and moving, which gives you about 300 hours a year that you're designing the conventional car, its electronics for. Whereas an EV is going to be charging potentially 2 to 3 hours for every hour that the car is driven on the road. And while it's charging, all those systems have to be thermally managed. To understand the impact of it, this is the type of durability curves that show up on semiconductors and electronics. Whereas, as you control the temperature and you manage to get it, as you manage to take the temperature from being excessively hot, like you see on the right-hand side of the chart, you will get increasing life that goes up quite dramatically. And this is essential to do at all times in all conditions of the car, or this accumulated damage will mean that the vehicle fails early in its lifespan. So these are the needs. And with these needs, there's possibilities on making a better car. Now, Exa's thermal management solution can meet these needs and provide ways to deal with all of them. We can help you simulate and analyze the effects of these real-world conditions on the parts that are in the vehicle. Because these can be accurately simulated early on, this provides the opportunity to put complex pieces together that are just not possible before prototypes are done, are not possible using other solutions before prototypes are available. We can look at the interactions that are driven thermally, evaluate that early when there's still an opportunity to make significant improvements in the design and have the confidence they're going to behave and provide the benefits expected. Finally, none of this is happening by a team that works on one part. This is the entire vehicle team working together. And these solutions are built so that the entire team can understand what's being done and collaborate on it, looking at the vehicle before it's ever built. Exa solutions are multidisciplinary. They provide high levels of automation so these answers can be found repeatably and reliably, and most importantly, they're validated. So the capabilities we have are validated to provide the design capabilities needed to make these decisions with high confidence. Now, to understand how they're used, you need to look at the development process that's typically going to happen in building a battery pack. The development process starts with a beautiful sketch of what the car is going to be and a list of ideas of how that car should behave, how it's going to accelerate, what kind of fuel economy it should get, expectations on what its durability is going to be, and finally, one of the ones that's very sensitive, cost. To make that happen, especially when you're electrifying a vehicle, one of the first choices is to take a look at the powertrain architecture. So this is how you take the energy that you have in the vehicle, whether it's gasoline or electric, and you get it to the wheels to make the wheels do what you want. There's a lot of different solutions that are out there, everything from what's known as a mild hybrid, where the engine stops and starts, to a full hybrid, where the electrification can provide engine off operation. There's plug-ins, which primarily provide engine off operation. And we're focusing on today electric vehicles. But based on this choice, you then can figure out how the battery electrical power is going to be delivered. And the battery electrical power comes in terms of the peak amount you need to provide. So when the car accelerates, there's a peak amount of power that's required, the capacity, how much power or how much energy you will need to carry the car the distance you expect, and then finally the efficiency of it. Once that's understood, there's decisions to be made on what the battery supplier is going to be, what the chemistry is going to be, and even the form the batteries are going to take. And all of those then open the stage for taking a look at how you're really going to manage this. And that gets to the thermal architecture choices. So with the thermal architecture choices now, we have the amount of batteries, we know the battery we need to handle, we have the goals for it, and we have to figure out how to get out the heat that occurs as it's being operated. And there's basically three major choices, one of which is there's some form of a cold plate or liquid cooling, there's forced air, and even in some cases there's manufacturers deciding to do nothing and just rely upon the thermal inertia of the batteries to provide the energy absorption and the release during the driving. Once all of this has been done, the analysis complete, then the goal is to prove that this works and does what's expected. And that's where these simulation solutions provide the strength, is when these decisions at a very low level are made, we can prove that they work at a vehicle level, the same as what happened with the prototype. We support the key decision makings from powertrain architecture through battery architecture, through thermal architecture solution, and provide the tools to help make better solutions and choices in each of those. Now, the way this works is a battery is not just a thermal system, it's not just an electrical system. So we have a solution which allows us to start with the electrical characterization. Working with the supplier, working with internal test labs, the battery can be characterized to understand how it behaves, what its losses are. 3D cell models can be generated. Those can be integrated into modules, which are collections of cells. Those can then be put together into packs, which is going to provide the tractive energy for the car. And to support physical testing, we can also convert those packs into forms that can be used as virtual batteries for physical testing. And then finally, we can put all this together to provide a 3D vehicle simulation and to provide system models that are tied into those 3D battery models to look at the operation of the vehicle in various environments and conditions. Diving into this a bit, before you hit the batteries, one of the things you have to worry about in an electric vehicle is how the electronics and wiring are going to be managed. So we have solutions that allow you to take a look at the local current density, the impact of the local current densities and voltages on component self-heating. We have the solution looking at the conduction and the radiation and either natural or forced convection, which is driving the heat flow through these sensitive parts. Now, EVs are being used are introducing not just power electronics, but they're also tending to be paired right now with autonomy and high performance computing power, which drives the need to put cooling systems in cars that traditionally have not been there. And once you've got the simulation capability, then it's possible to do things like take a look at the impact of changing wire gauges. So should you be putting a higher wire gauge in to help make sure that the electrical system is going to be durable? Take a look at the impact of enclosure shapes and positions and locations in the car, and even the layout of the heat sources and the cooling system. With that, providing a boundary condition or interacting with the boundaries of the battery, we get to the battery model. One of the key points is the battery model really can't be separated off into an electrical and a thermal part. When the electrical part of the battery generates heat, that changes the temperature of the battery. Changes in the temperature of the battery change the electrical performance. So for the highest accuracy, it's necessary to couple these two parts when building a simulation. And to give an example of it, this is a validation case that was done many years ago to prove out the accuracy of the solution. And it shows how you can end up with complex flow fields driven by blowers and jets inside the battery pack, how those in turn can interact with the electrical duty cycles that are being applied to the battery and lead to highly dynamic temperatures, both spatially and temporally, across the battery. To help drive that heat model, we have an electrical model. As mentioned earlier, the capability allows us to take lab or field test data that may come from the supplier, may come from internal labs, may even come from the vehicle in operation. That's then turned into a large-scale optimization problem, which in turn allows us to fit an equivalent model. It basically looks like an equivalent circuit that then can be used to drive the thermal behavior and to look at the reaction to the temperatures in the battery. Given that electrical model, now it's possible to move on to doing cell development. So with cells, there's typically manufacturing choices that the supplier has that allow them to make simple changes in the aspect ratios or the materials that are used in the battery that will affect the local current, that will affect the local current density. By affecting local current densities, that affects the local heating. And then you can look at the effect of doing things like changing tab sizes, tab location, the overall area of the cell, the thickness of the cells, and much more. putting this together into a module and simulating this on a drive cycle, it's possible to take a look at the different shapes that the cells come in, pouch, prismatic, or cylindrical are the three common ones, and simulate with the boundary conditions of the current and the thermal environment to predict the temperature, the voltages, and the state of charge as one integrated model. Now, 3D models also need to drive other activities in an OEM or any team designing for batteries. So the full 3D simulation can be translated into a system model. And this has a lot of advantages with the workflow within an organization, because if you don't have this coupling from the 3D model to the system model, you have two teams which are trying to coordinate through ad hoc methods. Our methodology allows us to take that 3D model, as the geometry changes are made, create a system model, and then provide that system model to other parts of the organization, maybe doing control work, physical testing, or overall system analysis. To provide an example of what kind of benefits this offers, this shows an example of a battery being exercised over several hours through a testing cycle. The battery is then allowed to rest for a while, and then the battery is charged and eventually topped off. So you can see that on the graph on the left. You can see the dynamic changes in the current, and then you can see how it goes into charging. And the result is all this usage of the battery causes the temperature to increase, then it cools down as the battery is turned off, and then as the battery is charged, the temperatures pick up again. To do this in a full 3D model for this type of system, this may take, say, 13 hours to do the simulation. By doing simplifications in the 3D model, which the solution offers, we can accelerate that by a factor of 10, now actually having a faster than real-time solution. And by doing another reduction to turn it into a system model, we're now able to get almost 10,000 to 1 improvement in turnaround time in execution speeds, so that we can effectively match what we see in the simulation of 3D for critical aspects and provide that fast model support other analyses. Now, we talked earlier, there's a lot of choices on how the battery pack is going to be cooled. The two big choices are typically air cooling with some kind of forced air and liquid cooling. With the air cooling, the air is blown over the batteries and forced convection is used to extract the heat. With liquid cooling, a cold boundary condition is applied to the bottom, and that provides the cooling that keeps the battery in a desired temperature range. And if we look at the results of this, we can see that they have their different advantages. An air cooling system actually tends to be much lighter. It's typically tied into the cabin, and it's typically used for light-duty hybrid electric vehicles, and even some other applications that are more industrial. And then liquid cooling is preferred choice that's being used right now for most pure electric vehicles, because it tends to offer overall a better performance. To support that, we have the ability to take a look at the flows that occur inside the cooling system. Then, given those flows, look at the heat transfer and look at how that pulls the heat out of the battery. So on the left here, you see the flow. As it develops, you see it turning into an ability to pull the heat out of the battery, and this in turn gives us a temperature distribution between the battery and the cold plate, which is driven by this flow field. Finally, it's important to be able to look at lots of different architecture choices quickly. So when you're considering the battery pack, there's many, many ways that, given the volume that the batteries are going to go into, they can be laid out. And we have tools that make it very quick and very easy to consider different battery layouts, so that in turn that can go through the rest of the analysis, and you can look at competing physical architectures at the same time you're looking at trade-offs in other areas of the pack. Finally, we talked about this earlier, the full vehicle can be put together. And this is actually one of the toughest problems we're showing right here to look at for a battery, which is a battery coupled to the cabin and subjected to solar loading. As the heat builds up in the cabin, gets a stratification of temperatures inside of there. We have large amounts of conduction through the structure, and we have the soak from the air in the cabin driving the pack temperatures. And as we look at this, we can see that something that may happen over 12 hours can drive the battery temperatures to potentially undesirable ranges. And then this information can be used to make choices in the cabin design and the thermal management of the pack, so that you have a better, more robust, and more durable EV. So this all opens up a potential, and that potential drives the success that can be had in doing the design correctly. So to show what goes on in an EV design, we just kind of wanted to walk through the transition to go from a conventional vehicle to an electric vehicle. So this is showing a conventional vehicle here on a track. We see the airflow going under the hood, going through the cooling package, cooling off the engine, and the goal is to go from something like this to an electric vehicle. Well, every change that needs to be made to make an electric vehicle is a lot more than skin deep. This is an example of a powertrain in a conventional vehicle right here. It's got a lot of design management issues that are driven by the high temperatures that the engine operates at and the protection that needs to be in place to keep those high temperatures separated from the rest of the vehicle. By the way, we're really good at solving this problem too. The other challenge you have is that on a conventional vehicle, you're used to getting rid of large amounts of heat. And in fact, when you're running an engine, only a small fraction of the energy in the gas makes it to the wheels. Another big fraction has to be pushed through the cooling package. And this requires airflow at the front of the car, lots of airflow that impacts drag, that impacts performance of the engine, and there's trade-offs involved in that. We're good at helping with this problem too. With an EV, this changes. So the cooling package changes. We mentioned earlier that the suspension system, well, the battery pack's a lot heavier, so the suspension needs to change. And then by the time we get down to it, because an EV can do something that a conventional car can't do, it can pull energy out of the wheels and pull it back into the batteries. It actually opens up opportunities for more efficiency, lighter weight brake systems. So literally everything on the car changes, and also the tires are typically changed. So let's start putting together our EV now. We've almost got a clean sheet of paper. We have to add the batteries. Well, the batteries have to fit in a way that they're not going to interfere with cargo, passengers, and everything else, and be packaged safely. Center of the car is a great place to put a battery pack. Build new structures around it. Seal it up. Add the propulsion system. That's the electric motors that help make the car move. Add the cooling system. And in fact, one of the interesting things is, as we look at putting EVs into place, because there is so much energy that's diffusely having to be gotten rid of by the cooling system, we actually have much more expansion in the cooling system itself. This is showing the cooling system now going through the inverter to keep the power electronics cool, going through the motor to keep the motor cool, and going through almost the entire underside of the car in this case to keep that battery pack cool. This is a big engineering challenge to make that work right and make it durable. Well, we seal all this up and make sure that the car is going to hold together. And then finally, because we have changes in how the car is being used, what the thermal needs are on it, we actually get opportunities to make improvements in aerodynamics even without making a major change in the car, because the airflow required for cooling is much lower. So that's it. That's the transition from an ICE to an EV. Those are the challenges and opportunities. And every one of these is a place where somebody can innovate. And these tools that we offer will help you create that. So I'd like to thank you for joining us. And with that, any questions, please provide them through the chat.
Great. Thank you, Ed. We now have a few minutes for Q&A. Ed can take your questions if you type them into the Q&A window in the lower right-hand corner of your screen. We do have a few already rolling in here. So the first question we have, Ed, has to do with, does this work with all batteries?
Yes. I mean, one of the key steps is that we use experimental data off the battery chemistry, and from that we're able to drive the thermal models. So we can deal, any chemistry you give, we can help out with.
Great. Okay. The second question we have is, the battery has to be kept within an optimal range, just like you said. It can't be too hot and it can't be too cold. How do you handle that within your solution?
To figure out what's happening with the battery, the key aspects are what is kind of like the average temperature you've got, and what are the hot spots that are in there that may affect the battery aging. So to do this, we build full 3D models. So down to the detail of each cell is individually put into the model. That's then all integrated up to give you the full pack, just like we showed with the geometry that was there. And that in turn allows you to make those predictions.
Great. Okay. Another question. Back in the section on the system model versus 3D model comparison, how did you make it go so fast, and what compromises are you making?
Okay, that's a great question. First off, it's understanding why you're doing the system models. The system models are usually focused just on a small set of behaviors that appear. So when we generate the system models, they are designed to provide things like a reproduction of what a thermal sensor is going to have, like a thermistor, and provide that sort of feedback. So we focus on hotspots, we focus on critical control parameters, and then by doing these simplifications, we're able to build this model that captures that as essential behavior.
Okay. We have another one that's come in. In winter, can you dump the battery excess heat into the cabin? That's the similar way you would lower the cost of heating for a traditional vehicle.
Okay, well, the second comment there, I think there's two things you're looking for. Number one, yeah, the battery can act both as an electrical and a thermal battery. That's something a design team would have to look at the trade-offs in it, but while charging, it would be possible to keep the battery warmer, and then it would also be possible to pull some of that heat out of the battery, push it back through the cooling system, into the HVAC system, and eventually into the cabin. Once again, when you look at that, that's something that is a complex system interaction, and these tools would help you understand. The second part of your question, I think, was, is it possible to recover heat from the operation? So when you run a conventional vehicle, you've got a very rich source of heat on a cold day. The engine's throwing off a lot of of heat that never makes it to the wheels. EVs are a lot more efficient, so that heat's not nearly as high. The temperatures are much lower, and the quantity of heat is generally much less. Now, what can be done is things like heat pumps to turn it into the temperature range that's needed, and eventually provide that to somebody in the cabin for comfort.
Okay, great. Thanks. Okay, so far we just have one more question, so if you have any last-minute questions you want to get in, please type them in your Q&A window in the lower right there. The last one I have here is, there's so much here. Where should I begin if I just want to get started with thermal simulation?
Okay. The key part in electrification is going to be the batteries. So a great entry point is just looking at the batteries that are being put into your system and start with very simple assumptions. These can all be made before any testing or anything else is done. And this looks like just a traditional thermal protection problem. And then from there, each of these additional capabilities can be added on to give you increased accuracy and capability in your design work.
Okay. We do have one more that came in. Be sure and send them along. We're about to the end of our time here. Does your model include the coolant, hydraulic characteristics, flow rate, and temperature?
Well, simple answer is yes.
Okay.
So, and anything else you'd like to take a look at in that, we also can provide the design information needed to make that system move forward. All right?
Great. Thank you. That's it for question and answer. Thank you so much for joining us for this webinar, and we hope you stay tuned for future EV webinars on EV design from Access. Thank you and have a great day.